Your Moodle site might look perfectly healthy while its login sessions and much of its cache are still stored on disk. In this video, we will move both to Redis. Then we will prove that Redis stays private, the data survives a graceful restart, and purging MUC does not log out an active user. I won't invite a speed percentage from an idle demo server. We are going to build a configuration we can see, test, and explain. Welcome back to Open Education Operations. Redis is an in-memory data store, and Moodle can use it for two separate jobs: browser login sessions and Moodle Universal Cache. Moodle also has a MUC cache type named session. That name is easy to confuse with the user session handler in config.php, but they are separate mechanisms. For this demonstration, Redis will run locally on the same VPS as Moodle. This is a single server design, so it does not provide high availability. Once Moodle depends on Redis, an outage can affect authenticated users and cached application data. Changing the user session backend also makes the old file-backed sessions unavailable. On a real site, schedule a maintenance window and warn users that they will need to sign in again. Before making these changes, create and verify a current recovery point. For the session checks, use a dedicated non-administrator account instead of an everyday user account. The companion guide will include the full prerequisites and rollback procedure. Let's get to work. Before adding a new service, we need to confirm the starting point. Redis is not installed, the PHP extension is absent, and Moodle has no Redis configuration. I will start in my SSH session with a read-only check. It reports the Redis package, service, PHP extension, listener, and Moodle configuration state. The result confirms our clean starting point. The package, service, and PHP extensions are absent. Nothing is listening on port 6379, and Moodle has no existing Redis configuration. Now let's check Moodle. I will open Site Administration, select Plugins, and in the Caching section, I will click on Configuration. Under Installed Cache Stores, Redis might appear as an available plugin, but there is no configured ready-to-use instance yet. Further down, under Stores used when no mapping is present, Application caches use the default file store, MUC session caches use the default session store, and request caches use the default static request store. So Moodle is still using its original cache configuration. With the baseline confirmed, I will return to SSH. Before modifying config.php, I will create a root-only directory and save a rollback copy there. If the edit causes a problem, I can quickly restore the original configuration, so this is a good practice. With the protected directory ready, I will copy the current Moodle configuration while preserving its metadata. Before moving on, I will verify the directory and file permissions. The directory is accessible only to root, and the copied file keeps its original permissions. We now have a clean baseline and a quick rollback copy, so we can install Redis. Technically, we need two pieces: the Redis service and the PHP extensions that let Moodle communicate with it. I will install both and check them before Moodle depends on them. First, let's refresh Ubuntu's package index. With the package index current, I will install the Redis server and the php-redis extension from Ubuntu's repositories. The server package also gives us redis-cli for local checks. The extension is installed, but Apache needs a reload before Moodle can use it. The reload returns directly to the prompt. Now I will check that Redis started correctly and responds locally. In this command, I will verify three things together. Redis is running, it is enabled for boot, and it answers a local command. Redis is active, enabled, and returns Pong. Local connectivity works. One more installation check remains before we can move to the network boundary. I will confirm that PHP can see the Redis extension and the optional IG binary serializer in its command line runtime. Later, Moodle's cache page will confirm that the web runtime can see it too. Great, the Redis extension is loaded and IG binary is available in this environment. Now Redis is awake, but before Moodle gets anywhere near it, let's make sure it hasn't found its way onto the public internet. Redis answered our local ping, so we know the server can reach it. Now we need to verify that access stops at the server boundary by checking the configuration, the live listener, the firewall, and finally an external connection attempt. I will begin with the configuration file and read the active bind, protected mode, port supervision, and snapshot directives. The bind directive contains only loopback addresses. Protected mode is enabled, the port is 6379, and RDB save points are configured. Ubuntu's package configuration already matches this local-only design, so no change is needed here. But a wildcard or public bind address would be a reason to stop and check before moving on. The configuration shows where Redis should listen. This command shows where it is actually listening. Great, Redis is listening only on loopback, not on a public or wildcard address, so we can move to our third check. Because Redis is local only, it should not have an inbound firewall rule. That means I need to confirm that port 6379 was not added to UFW. The existing SSH, HTTP, and HTTPS rules remain in place, and there is no rule for Redis. This is the result expected in my setup. Now the last one. The server-side checks looks correct. For the final boundary test, I will switch to a PowerShell session and attempt a TCP connection through Moodle's public hostname. The result shows port 6379 and TCP test succeeds false. Redis answers locally with pong, but the external TCP connection fails. So now we can see that the listener, firewall, and external tests all agree. Redis is healthy and reachable only from this server. We can now connect it to Moodle without exposing a new public service. Let's do it in the next step. We will move browser login sessions first. Existing file-backed sessions will no longer be recognized after this change. So we need to enter maintenance mode before config.php is edited. Back in SSH, using this command, I will place Moodle in command line maintenance mode to block normal web requests, while the session backend changes. With maintenance mode enabled, I will now open config.php and move to the bottom of the file. Here I will find the line that loads lib/setup.php. I will add the Redis session configuration immediately above it, because Moodle needs these settings before its setup process begins, so make sure to make this change in the right place. The handler selects Moodle's Redis session driver. The host and port point to the local service. Database 0 is explicit, and OpenEduOps _US_ gives the user session keys their own namespace. We are not adding a password because this Redis service accepts connections only through the server's loopback interface. Please do not copy that choice to a remote Redis deployment. Now let's save the file and exit Nano. Config.php is critical, so before reopening the site, I will check that PHP can parse the file as the www-data account. If the check fails, keep maintenance mode enabled until the file is corrected. PHP reports no syntax errors, so the new block parses correctly. Next, I will make sure the edit did not change the file permissions. The Redis block contains no secret, but the rest of config.php still does. So this is very important. The result remains as expected, so editing the file did not weaken its permissions. After both checks pass, I can reopen Moodle and create a real browser session through the new Redis handler. But before this, I need to disable maintenance mode using this command. Great, Moodle is available again, so I will leave SSH for a moment. Now I will open a fresh private browser window and visit my Moodle site. I will sign in with a student account, open the dashboard and refresh it once. I will leave this authenticated session active so we can test the same session after the Redis restart and the cache purge. A fresh sign-in is expected because the old file-backed sessions are no longer active. The dashboard loads normally, confirming that Moodle can complete an authenticated request through Redis. Back in SSH, I will count the keys under the configured user session prefix. The exact count here will change and does not represent the number of users. What matters is that the user session prefix contains data after the authenticated browser request. Browser sessions are now using Redis under their own prefix. Next, we will connect Moodle's cache framework and give its keys a separate namespace. With browser sessions now using Redis, we can move to MUC, Moodle's cache framework. MUC stores reusable application data, so the site does not have to rebuild or fetch the same information on every request. One detail is easy to mix up. MUC includes a cache type called session. That is not the browser login session handler we configured in config.php. It's same name, but definitely different job. Now, again, back in Moodle, I will return to the cache configuration page. Under installed cache stores, the green check beside Redis confirms that Moodle's Apache PHP runtime can use the extension. In the Redis row, I will select Add Instance. I will name the store local Redis and leave cluster mode unchecked. For server, I will enter the loopback address at port 6379. TLS encryption stays unchecked, and both the CA file path and password stay blank because this connection never leaves the server's loopback interface. For the key prefix, I will enter OpenEduOps _CS_, keeping MUC cache store keys separate from the OpenEduOps _US_ used for user session keys. Under Use Serializer, I will select IG binary serializer, and I will leave Use Compressor set to no compression. If IG binary is not available in another environment, keep Moodle's default PHP serializer instead. And because Redis is local, the connection should be almost immediate. I will keep Moodle's 3-second connection and read timeouts. They prevent a Redis problem from leaving requests hanging for too long, and they are a reasonable starting point for this single server setup. For remote or clustered Redis, test the values against your real network latency and failover behavior. Now I will select Save Changes. After saving, I will return to Configured Store Instances and find local Redis. The plugin is Redis. The green check confirms the connection is ready, and mappings still show 0. We have created the store, but no cache type uses it yet. Next, under stores used when no mapping is present, I will select Edit Mappings. For application, I will select local Redis. For session, same, I will select local Redis. I will leave requests on default static store for request caches, because Redis is not fully compatible with every request cache definition. After saving, I will return to stores used when no mapping is present. Application and session now point to local Redis, where request remains on the default static request store. The mappings do not replace the browser session handler. Its separate path still comes from config.php and still uses OpenEduOps _US_. Now I will switch to the existing authenticated student session and refresh again the dashboard. Then I will open one course page and return to the dashboard. The existing session remains valid, and this normal page activity gives Moodle a reason to populate its newly mapped caches. We will use this same active session again later. Those page loads have now used both Redis paths. So back in SSH, I will count the user session and MUC keys separately and check for anything outside the two configured prefixes. These counts will change as sessions expire and caches rebuild. They are not user counts or cache definition counts. What matters is that both prefixes contain data and nothing unrelated appears in this dedicated database. Next, we will restart the service and check whether that state survives. Redis now handles the login paths. During the restart, Moodle will briefly lose access to active sessions. So I will block new web requests while the existing browser session stays idle. First, let's again enable maintenance mode. Next, I will restart Redis gracefully. In this Ubuntu configuration, the service saves the RDB dataset and reloads it during the restart. The command might return no output, so I will verify the result in Redis and then test the active browser session. So I will check whether both Moodle namespaces returned after the restart using this command. Great, Redis is running. Pong succeeds, both namespaces are back, and the persistent status is clean. The checks pass, so I will disable maintenance mode and reopen Moodle. With the site available again, I will refresh the existing authenticated browser session, open the course page, and return to the dashboard. We are doing the same test as before. The account remains signed in, so the same session survived the graceful Redis restart. This confirms persistence for the graceful restart we just tested. This is still one Redis service, not high availability. Moodle can be interrupted while Redis is unavailable. The restart preserved both namespace. Now another test. We will purge Moodle's caches and confirm that the separate login session survives. Moodle should be able to discard and rebuild cache data without deleting the authenticated browser session. The separate prefixes lets us test that directly. Before touching the caches, I will return to my SSH session and count the two namespaces again. Both namespaces contain data before the purge, and no unrelated key appears in the dedicated database. Now I will run Moodle's official command line cache purge as the www.data account. It clears rebuildable Moodle caches without using Redis/all or touching the separate user session prefix. The command might return no output, so I will check Redis and then test the active browser session again. So first, let's inspect both Redis namespaces immediately after this purge. The MUC count may already be above 0 because Moodle and the CLI can begin rebuilding cache data during the operation. The user session namespace is still intact. The MUC namespace may already contain rebuilt keys, and there are still no unrelated keys in this database. The Redis side result looks right. Now I will refresh the same authenticated browser session, open the course page, and return to the dashboard. Yes, sorry, we did it again. The account remains signed in, confirming that the MUC purge did not invalidate the separate Redis-backed login session. After this normal page loads, Moodle should have started rebuilding the MUC namespace. Back in SSH, one final count, and this time I promise, this is the last one. The MUC count does not need to return to its earlier value. Caches rebuild when Moodle needs the data. The important result is that MUC resumed normal use while the authenticated session remained intact. To finish, I will capture a Redis health snapshot in SSH. It covers memory, clients, errors, persistence, and recent warnings, not performance. Redis is using little memory on this host. There are no blocked clients, rejected connections, or evictions. The last RDB background save succeeded, and no new Redis warnings appeared during the test. An important note, the hit and miss counters only describe this short test. They do not prove a speed gain. And at this tiny memory footprint, a high fragmentation ratio alone is not a reason to start tuning Redis. The service looks healthy. Before closing, I will repeat the live listener check and confirm that Redis still listens only on loopback. For one last boundary check, I will return to my PowerShell session and repeat the connection test. The listener remains private and the external connection still fails. This is great news for us. Moodle is now using a private local Redis service for two separate jobs, login sessions and MUC. We confirmed that it remains private, survives the graceful restart we tested, and lets Moodle purge and rebuild its caches without logging out the active user. This is a single node setup, not a performance benchmark or a high availability design. The companion guide includes the complete commands, rollback, and troubleshooting steps. If this helped you understand what Moodle is doing behind the interface, subscribe to Open Education Operations. I will see you in the next one.